Hello, we're group number 4, and today we'll be presenting our final lab on PPG signal acquisition and analysis. These projects integrate ECG and PPG signals to analyze cardiovascular health, calculate pulse transit time, and determine arterial stiffness using pulse wave velocity. The main objective of this lab was to understand cardiovascular physiology by analyzing ECG and PPG signals. We focus on measuring the pulse transit time, which is the time delay between the heart's electrical activity seen in ECG and the blood flow response, captured by the PPG. This analysis helps us to explore arterial stiffness and its relationship to blood pressure using PWV calculations. Additionally, this lab allows us to gain hands-on experience in building a PPG system, processing signals using MATLAB, and synchronizing data for accurate results. For this experiment, we use an Arduino connected to a breadboard to build a PPG circuit. A green light illuminated the fingertip, and a photoresistor detected changes in light intensity due to blood flow. Resistor and jumper wires were ensured proper circuit functionality. To capture ECG signals, we use a BIOPAC system, and for data processing and analysis, we use MATLAB software. We designed a simple PPG circuit where the green LED illuminated the participant's fingertip, and the photoresistor beneath the finger detected blood volume changes as variations in light intensity. The circuit was connected to the Arduino for data acquisition. The ECG signals were captured separately using the BIOPAC system, with electrodes placed on the participant's left wrist and both ankles. Together, these two systems allow us to synchronize and analyze the data for PTT. Here, we can observe our experimental setup. The participant is seated with the BIOPAC electrodes placed on their ankles and wrists to capture ECG signals. The Arduino and PPG circuit were connected to the computer, running MATLAB for data acquisition. The participant remained still through the process to minimize noise and motion artifacts. To acquire the signals, the BIOPAC system captured ECG signals for 30 seconds, while the PPG signals were recorded using the Arduino and MATLAB. We applied pre-processing techniques to filter the data and identify key features, especially the R-wave peaks were detected in the ECG signal, and the pulse foot markers were identified in the PPG signal. This image shows the raw ECG signal acquired using the BIOPAC system. You can see consistent R-wave peaks, and the heart rate is also recorded over the duration of the experiment. Once the signals were acquired, we applied pre-processing methods in MATLAB to clean and analyze the data. For the ECG signal, we use a bandpass filter to remove noise and accurately detect the R-wave peaks. For the PPG signal, a low-pass filter was applied to smooth the waveform and identify the pulse foot markers using a second derivative method. Here is the filtered PPG signal. The pulse foot markers, which are critical for PTT calculations, have been clearly identified and annotated. The results for our analysis are summarized here. By synchronizing the ECG and PPG signals, we calculated an average pulse transit time of 0.1080 seconds. Using this value and assuming a distance of 0.6 meters between the heart and the fingertip, we derive a pulse wave velocity of 5.56 meters per second. The average heart rate calculated from the heart wave peaks was 85.6 beats per minute. This figure shows the filtered ECG signal with R-wave peaks and the PPG signal with annotated pulse foot markers, demonstrating the features used for PTT calculation. And on this table summarizes our numerical results, including PTT, PWV, and heart rate values derived from the signals. During the experiment, we observed clear and consistent R-wave peaks in the ECG signal, which reflected normal heart electrical activity. The PPG signal exhibited distant pulse foot markers with minimal variability. Proper synchronization between the two signals allow us to obtain stable PTT values. Additionally, we noted that accurate sensor placement and minimizing participant movement were critical to reducing noise and motion artifacts. Our calculated values of PTT of 0.1080 seconds aligns with typical physiological ranges. This value represents the time delay between the heart's electrical activity and the arrival of blood flow at the fingertip. The corresponding pulse wave velocity of 5.56 meters per second suggests normal arterial compliance, as higher values would indicate arterial stiffness. Challenges included minor motion artifacts, but we mitigated these issues using robust filtering methods in MATLAB. Overall, this experiment demonstrates the potential for non-invasive cardiovascular monitoring with applications in wearable health devices for real-time assessment of blood pressure and arterial stiffness. Now we will show a brief video demonstrating our experiment. This video captures the entire process, including the participant setup, signal acquisition using BIOPAC and Arduino, and real-time data visualization in MATLAB. In conclusion, this experiment successfully combined ECG and PPG signals to analyze cardiovascular function through pulse transit time and pulse wave velocity. The results highlight the feasibility of using these non-invasive methods to assess arterial stiffness and blood pressure trends. Future applications could include wearable devices for continuous cardiovascular monitoring, making this technology accessible for real-time health assessment. Thank you.